Right now, billions of transistors in your device are switching on and off, millions of times per second. And every single one of those switches runs on electricity. We use it every day. We charge our phones with it. We get shocked by it touching a doorknob. But almost nobody can actually answer a simple question. What is electricity? Not the definition from a textbook. What is it physically at the level of matter itself? That's where this series begins. Because if you want to understand how a computer works, you have to start here. Everything around you is made of atoms. Your chair, the air, the screen you're watching this on, all of it, atoms. And every atom has three kinds of particles inside it. Protons, positively charged, sitting in the nucleus at the center. Neutrons, no charge, also in the nucleus. And electrons, negatively charged, orbiting around the outside. In a stable atom, the number of protons and electrons are equal. The positive and negative charges cancel out. The atom is balanced. But here's the thing about electrons. They sit on the outside, and in some materials, they're loose, not tightly bound to their atom. They can drift from one atom to the next. These materials are called conductors. Copper, gold, aluminium, metals mostly. In a conductor, electrons are always slightly moving, wandering, drifting, bouncing around. Other materials hold their electrons tightly. The electrons cannot move freely. These are called insulators. Rubber, glass, plastic. When you look at a copper wire wrapped in plastic, the copper is the conductor, electrons move through it, and the plastic is the insulator. It keeps the electrons from escaping. So electricity is the movement of electrons through a conductor. That's it. Electricity is not a fluid. It's not a gas. It's electrons, already present in the material, being pushed in the same direction. But what pushes them? That force, that pressure, is called voltage. Think of voltage like water pressure in a pipe. The higher the pressure, the harder the water is pushed. The higher the voltage, the harder the electrons are pushed. Voltage is measured in volts. Your phone charger, around 5 volts. A wall socket in Europe, 230 volts. A lightning bolt, up to 300 million volts. Voltage is the pressure, but pressure alone doesn't move anything unless there's somewhere to go. If you push electrons through a conductor that connects back to where it started, you've made a circuit, a closed loop, and electrons flow around it. The amount of electrons actually flowing, the rate of flow, is called current, measured in amperes or amps. If voltage is pressure, current is how much water is actually flowing through the pipe. A phone charging cable carries about 1 or 2 amps. A car battery, hundreds of amps. Together, voltage and current give you power. Power is voltage multiplied by current. Your phone charger, 5 volts times 2 amps equals 10 watts. Your microwave, around 1000 watts. Power is how much work electricity can actually do. Now let's build the simplest possible circuit. A battery, 2 wires, and a light bulb. The battery creates a voltage, a pressure difference between its positive and negative terminals. Connect the wires. Electrons feel that pressure. They flow from the negative terminal, through the wire, through the bulb, and back to the positive terminal. As they pass through the bulb's thin filament, the filament resists. The electrons have to force their way through. That resistance generates heat. Enough heat, and the filament glows. Light. That resistance to electron flow is called resistance, measured in ohms. And these three things, voltage, current, and resistance, are connected by one of the most important rules in all of electronics. Ohm's law, voltage equals current multiplied by resistance. Push harder, more current flows. Add more resistance, less current flows. Every electronic device in existence, from a toaster to a supercomputer, obeys this law. So we have electrons. We have conductors to move them through. We have voltage to push them. We have current measuring how many flow. And we have resistance controlling how hard it is to push through. But here's the question that leads us all the way to computers. What if we could control the flow? Not just let electrons move freely, but switch them on and off. Let them through or block them. On or off. 1 or 0. That single idea, controlling the flow of electrons, is the entire foundation of computing. Everything your computer does, every calculation, every image on screen, every word you type, it all comes down to whether electrons flow or don't. A computer is not magic. It's not mysterious. It is very precise, very fast control of electricity. Billions of tiny switches turning on and off, millions of times per second. And those switches have a name. In the next episode, we're going to meet them. We'll start with the first version, a mechanical relay the size of your fist. We'll watch it evolve, and we'll arrive at a device so small you cannot see it with the naked eye, a device that changed everything.